Pythagorean theorem and some additional theorems involving the Pythagorean theorem. So you're like, well, didn't we learn Pythagorean theorem in middle school? Yes, you did. Are we going to go past that? Yes, we are. Okay? Anything that you learned in a previous math class that had something to do with geometry, we're going to learn it and then we're going to go past that. Okay? So this is just a reminder of what you learned in middle school. In a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. So in this example, r squared plus s squared is equal to t squared. The hypotenuse is always the one that goes by itself because, well, it's the biggest. So let's do a couple of problems. So here, our hypotenuse is x. You don't have to write it down, but you always have to identify which side is the hypotenuse because that's the one that goes by itself. So this will be 10 squared plus 14 squared is equal to x squared. 10 squared is 100. 14 squared is 225. No, that's 15 squared. 196 is x squared. So x squared is 296, which means that x is the square root of 296. Now, when you learned this in middle school, at this point you did one of two things. Either you just left it like this, unsimplified, or you chuffed it into a calculator and gave a decimal approximation. Okay, we are going to do neither of those things. We are going to simplify this square root, which is why we did simplifying square roots. So for the 296, I don't know about you, I don't immediately see a large perfect square that divides evenly into that. So I'm going to divide this up. That's 2. That'll go 4 times with 1 left over. That'll be 8. 2 goes into this 74 times. 2 goes into 74 37 times. Now, let's talk about when you're trying to find prime factors. For a number like 37, sometimes you're like, yeah, I don't know whether that's a prime number or not. Like you were asking, is 67 a prime number, right? Oh, you were asking, sorry. Is 67 a prime number? So here's the way to decide, well, how far do I have to check this? Do I have to check like every number below 67? No. In fact, you just need to check any number below the square root of 67. Now, the square root of 67, who knows what that is? I certainly don't. It's a little more than 8. Okay, well that means I only need to check numbers that are prime numbers that are smaller than 8. Here, for 37, this is just slightly bigger than 36. The square root of 36 is 6. So the only prime numbers I need to check are prime numbers smaller than 6. Well, that's 2, 3, and 5, all of which are easy to check. None of those go into this evenly. So 37 is a prime number. So that's going to be 2. I'll have the square root of 2 times the square root of 37 is the square root of 74. All right, for number 2, this time the hypotenuse is given to us, but it's still set up the same. X squared plus 5 squared is equal to 13 squared. That's x squared plus 25. What's 13 squared?
169.
Yeah, 169. Subtract, we get x squared is 144. So x is the square root of 144, which is 12. This is an example of something called a Pythagorean triple. A Pythagorean triple is three numbers that work in the Pythagorean theorem, and those numbers are all whole numbers. There is an infinite number of these, but there are some that I think come up often enough that it's worth your time to memorize it. Okay, and I told you my story the other day about multiplying. I'm not big on memorizing things, but I think it's worthwhile. The simplest one is the only one where they're consecutive numbers. 3, 4, 5 is a Pythagorean triple. 3 squared plus 4 squared is equal to 5 squared. That also means that any multiple of that, so for example, 6, 8, 10, or 9, 12, 15, you could keep going and keep going forever. You're like, why should I bother memorizing 3, 4, 5? Well, because if you get a problem that the two legs are 3 and 4 and you want to know the hypotenuse, you don't have to do any work. You just go, oh, it's 5, and you're done. Not required to show any work. I would memorize 3, 4, 5. I would also memorize this one, 5, 12, 13. They come up often enough to where I think it's worthwhile. By the way, these sometimes will come up on things like the SAT, PSAT, those sorts of deals. And you're like, yeah, but I've got a calculator, no big deal. Yeah, that's true. But those are timed tests. And so if you could look at it and get the answer rather than having to do a lot of work, it's worthwhile. The last one I'm going to tell you about, it doesn't come up super often, so I have it memorized, but I don't know that it's a big deal if you have it memorized. 8, 15, 17. All right, so let's look at this last one. So for this problem, you're like, I've got 3 different triangles, the 2 little ones and the big one. How the heck am I supposed to do this? Well, if I just look at the little triangle that has x in it, do I know 2 other sides? No. And if I look at the big triangle, it has x as a side, and I've got 2 other sides, but do I know the big triangle is a right triangle? No. So can I use the Pythagorean theorem? No. But we can use this triangle over here, because if this is a right angle, this angle must also be a right angle since those are a linear pair. And I can find this piece. Whatever you do, don't call it x. The name x has already been claimed and no one else can have it. You can call it whatever you want. A, B, Y, Bob, whatever it is you want. Okay? I'm going to call it A. So a squared plus 8 squared is equal to 10 squared. Oh, hey, look. Right there on our list of Pythagorean triples. That means A has to be what? It's got to be 6. Now, if you want to take the time to work it out, that's fine, but you certainly don't need to. All right, so if this is 6, then this other piece is 14. Now I can do the Pythagorean theorem on this triangle. So 8 squared plus 14 squared is equal to the hypotenuse x squared. 8 squared?
64.
64. 14 squared?
196.
196. That's going to be x is the square root of 260. It's certainly not a perfect square.
It is a cool. It is a clean number.
What do you mean by clean?
There's
It's
no.
kosher? What?
I don't know. It's something. There's none in the one space.
There's what?
I don't know.
Okay. So we can divide this by 2, and that's 130. Divide that by 2, and that's 65. 65 is divisible by 5, and that's 13. So I've got the square root of 2 times the square root of 2 is 2. And I've got the square root of 5 and the square root of 13 still left. So that's the square root of 65. The first two problems you might have done in middle school, although you wouldn't have simplified them. This last problem, probably not. I've written down the Pythagorean triples here. I forgot that I had this on this page, to be honest. I wouldn't have written them on the front. So, how triples can help you out, like on this one. If one leg is 8 and the hypotenuse is 17, how long is the other leg? 15. You don't have to show any work for that. You also don't have to show any work on this one. You're like, I don't know that triple. Well, what are both of these evenly divisible by?
5.
5. This is 5 times 4, and this is 5 times 3. The triple is 3, 4, 5. So the hypotenuse will be 5 times 5 is 25. But be careful about using Pythagorean triples. There is a triple that's 5, 12, 13, but is x 5 in this?
No.
Not a chance, because it's the hypotenuse. So on this, we'll have to just gut it out. 12 squared plus 13 squared is x squared. 12 squared is
144.
144. 13 squared, 169. What is that? 313? Hmm, 313. It's not divisible by 2. It's not divisible by 3. It's not divisible by 5.
11?
11, I kind of doubt it.
Oh, yeah. Wait, no, 11.
What about 7? No, 7 doesn't divide evenly into that.
9?
Pardon?
9?
9's not a prime number.
Yeah.
You're calling it?
Wait.
I think it can be divided by something.
17?
17? Could be. I don't think it is, but let's check. Let's see. That's only going to go in once.
Yeah, no.
90, 63. Oh, yeah. 17 times 9 is 153. Man, that was close. Yeah, I don't think it simplifies at all. I'll double check. Oh, yeah, it does not. That's going to happen sometimes. Again, how many numbers should you check until you get the square root of 313?
None. I know it.
Pardon?
All of them up to 15?
What would be something that would be close? It's less than 20, because 20 squared is 400.
Oh, 17.
17 is 3 what?
Oh, 3.
Pardon?
I go up to 15.
17 squared is 289.
18?
18 squared is 300 and something that ends in 4. 18 squared is 324. I'm supposed to know that one.
So 17 and below.
So anything below 17 is all you have to check. All right, let's go on. So the converse of the Pythagorean theorem and extensions of the Pythagorean theorem. You may or may not have learned these in middle school. I think in my 7th grade pre-algebra class we did them, but I don't remember. I've slept since then. So in a triangle with sides of A, B, and C, where C is the longest side, if C squared is equal to A squared plus B squared, it's got to be a right triangle because it fits the Pythagorean theorem. However, let's think about this for just a second. Let's say I started with a right triangle. You don't need to draw this. And I kept these two sides the same, but I made this side longer, but still kept it a triangle. If I lengthen this side, what's going to happen to this angle?
Coming up obtuse.
Yeah, it's going to become obtuse. It's going to look like this. The big side is too big for it to be a right triangle. So if C squared is greater than A squared plus B squared, the triangle is obtuse. And then conversely, if C squared is less than A squared plus B squared, the triangle is an acute triangle. And sometime in the distant past of my teaching, someone decided to call this the Goldilocks principle. Because sometimes the big side is too big, and sometimes the big side is too small, and sometimes the big side is just right. Which was kind of funny also because it made it a right triangle when it was just right. Yes, I know it's stupid. But have I remembered it for probably 30 years? Yes. Okay.
That's like a long time ago.
Thank you. Yes, I am
Thank you for
oldish
that.
at this point.
Thank you for that information, Kyle.
All right, so let's determine whether triangles with a given side length is acute, right, or obtuse. Before now, with the side lengths, all we could tell is if it was scalene, isosceles, or equilateral. Although some of you on one of the quizzes tried to tell me whether it was a right triangle, acute, or obtuse. But now we can actually do that. So how do we do it? Take the biggest side, 11, square it. I usually put a question mark because I'm not sure whether it's bigger, smaller, or equal to. 6 squared plus 9 squared. 11 squared is 121. 6 squared is 36 plus 81. Still, I'm not sure. I'm going to add these two together. That's a 7. It's 117. It's close. The big side is too big, so this triangle is obtuse. All right. For this next one, how do we know which side is the biggest side?
By what's it? Getting the square root that's equal to 6.
Yes, okay, I see what you're saying. Yeah, what can I take the square root of and get 6?
36.
So 6 is the square root of 36. So now they're all square roots and I can compare them. Which one is the biggest?
36.
Yeah. So it'll be 6 squared compared to the square root of 15 squared plus the square root of 11 squared. 6 squared is 36. What's the square root of 15 squared?
15.
15. That's the definition of a square root. If you square it, you get the original number. Plus 11, 36 is bigger than 26. So again, this is an obtuse triangle. Okay, questions about that?